We're now moving on to lesson number 3 from the probability chapter. And for this lesson, we'll be looking at mutually exclusive events. All right, so mutually exclusive events. When we have two events that cannot occur at the same time, we will call that mutually exclusive. So once again, if we have two events that cannot happen at the same time, then they're considered mutually exclusive. Another way of looking at mutually exclusive is that the two events don't have any common outcomes. All right, so let's take a look at this. All right, so in my Venn diagram here, A represents the red circle will represent event A, and the blue circle will represent event B. This is considered mutually exclusive because everything in A is not a part of B. So like A and B, they're not touching each other, so they have nothing in common. So this is considered mutually exclusive. So if I ask for the probability of A or B, this would simply be the probability of A plus the probability of B. All right, so when we have a mutually exclusive situation, then the probability of A or B is simply going to be the probability of A plus the probability of B. And the probability of A and B happening at the same time is going to be 0 because they're mutually exclusive. And that means two events cannot occur at the same time. So that's why we have a 0 here. All right, so they don't have any common outcomes. All right, let's take a look at a situation where we're not mutually exclusive. All right, so in this diagram right here, you can see that A and B, they do have a common section that is similar, and that's this middle part right here. So this is not mutually exclusive because they have some common outcomes, which is this region right there. Okay. All right, so when I talk about mutually exclusive, that simply means A and B, they cannot happen at the same time. And when I have a case where they're not mutually exclusive, that means there will be a common section where they do share a certain region here. All right, let's move on. Let's practice the concept of mutually exclusive. Indicate which of the following events are mutually exclusive. Okay, so we have a dice is rolled and we have a card is selected from a deck. Okay, so let's take a look here. All right, so when rolling a dice, these are the possible situations that we can have. An even number is rolled, an odd number is rolled, a 5 is rolled, and a number less than 3 is rolled. Okay, so for this question, we want to know which letters A, B, C, and D are mutually exclusive. And then we have some options for our cards, but let's focus on this question right here, the dice. Now remember, a dice has 6 sides, 1 to 6. And events A and B are considered mutually exclusive. So when you roll a dice, you could get an even number. But if you have an even number, it's impossible to get an odd number. So A and B are mutually exclusive. You can't have an even number and an odd number as a result when you roll one dice. It can only be one of the two. So they can't happen at the same time. So they're mutually exclusive. Events A and C. So event A is an even number is rolled, and C is 5 is rolled. So yes, A and C, they cannot happen at the same time. Once again, if you roll a dice and if you get an even number, that even number won't be 5 because 5 is considered an odd number. So if you roll a dice, you might get a 2. If you have a 2, then it's really impossible to get a 5. So A and C are mutually exclusive. They cannot happen at the same time. All right, now events C and D, they are considered mutually exclusive. Because if you rolled the dice and got a 5, 5 is never less than 3. So C and D, you can't have those two events happening at the same time. If you had D, for example, a number less than 3 is rolled. So maybe you got a 1. Obviously, 1 is not 5. So C and D, they really can't happen at the same time. All right, so hopefully those examples make sense. And let's take a look at the next example here. A card is selected from a deck. So we have several situations here. A card is a club, a card is red, an ace is chosen, a face card is chosen, and a spade is chosen. All right, so let's take a look at this and let's just see which situations are mutually exclusive. So events A and C are considered mutually exclusive. So a card is a club and a card is red. So yeah, it's impossible to have these two situations happening at the same time. And let me just bring out the deck of cards right now. All right, so here's my deck of cards. If you look at the club situation here, clubs are located down here in this bottom row right here, and event C is a card is red, and obviously if you look at the clubs here, the clubs are not red, they're black. The red cards are the aces, sorry, the hearts and the diamonds here. So it's impossible to have a club and a red card at the same time when you draw one deck from when you take out one card from this deck here. So definitely A and C are mutually exclusive. They cannot happen at the same time. All right, let's take a look at another example here. Events A and D are also mutually exclusive. A is a card is a club, and D is a spade is chosen, and that's right. There's no way that these two events can happen at the same time. So once again, if I bring out my deck of cards, the clubs are located at the bottom right here, this bottom row, and the spades are located, I guess over here, the top row. Spades are red. No, sorry, those are diamonds. Sorry, I think I kind of mixed up the order here. Event A is actually clubs, so I'm sorry, these are your clubs right here, and these are your spades down here. So I apologize for mixing up the different categories. So once again, A is a club, and these are your clubs, the second row. And the spades, which is event D, spades are at the bottom here. So I do apologize for mixing up those two categories, and I think I mixed that up in the first example too, but hopefully you still get the idea of mutually exclusive. All right, and finally we have events C and D are mutually exclusive. So C is a red card and D is a spade, and yes, those are also mutually exclusive. If you take a look at the deck again, C is a red card, so the first row and the third row, those are my red cards. But a spade, a spade is located at the bottom right here, so the spades, they definitely can't be red, so yes, they are mutually exclusive. All right, so I do apologize once again for mixing up the categories, and let's just move on to the next situation here. Okay. Oh, and sorry, events B and E are mutually exclusive. A face card is chosen and an ace is chosen. Yes, there's no way that you could have a face card and an ace at the same time, so those will be mutually exclusive. And I'll just bring out the diagram just to show you guys again. Here are my face cards on the right hand side. So every single category, every single suite has a face card, and my aces are at the far left hand side, so there's no way that an ace can be a face card, so they are indeed mutually exclusive. All right, let's take a look at non-mutually exclusive events. If two events are not mutually exclusive, then we have this formula: the probability of A or B equals to the probability of A plus the probability of B minus the probability of A and B. All right, so here's my diagram here. If we're non-mutually exclusive, then this is my Venn diagram. I will have a common area here, and the area of both circles combined is equal to the area of the red circle plus the area of the blue circle. Okay. So here's my red circle, and there's the common part. And then I have my blue circle, and the blue circle also has a common part. And then what I want to do is I want to subtract the common area in between so that I don't overlap my answer. So if I minus this common area, which represents this and this, like we don't need to add both of these at the same time. We can add just one of these, and that means I need to get rid of this. So in order to get rid of this, I need to subtract one of the common areas. So this and this, they would cancel out. And then if those cancel out, and if you could put this back together, you get, your circle again. We group the pieces back together and the areas will be equal, right? And there you go. So yes, if I want to find the probability of A or B for non-mutually exclusive events, I want to take the probability of A plus the probability of B minus the common area, and that will give me the probability of A or B. All right, so we're going to practice using this formula in our next few examples. All right, so we're going to finish off the lesson by going over a few examples now. All right, so a card is chosen. What is the probability that the card is a spade or a royal card? All right, so what's the probability of being a spade or a royal card? Now, the question is this mutually exclusive or non-mutually exclusive? Well, can a spade be a royal card? It can. So once I bring up my diagram right here, here's my diagram right here, and if I look at my spades, which is my bottom row here, you'll notice that the spades right here, I do have some spades that are face cards, so this is a non-mutually exclusive question. So what that means is I need to use the formula of probability of spade plus the probability of being a royal card minus the common area. Okay, so the probability of being a spade is 13 out of 52. The probability of being a royal card is 12 out of 52. And the probability of being spade and royal is simply going to be 3 out of 52. All right, so let's talk about how we got these numbers. Let me bring out my deck of cards again. So the probability of being a spade is 13 out of 52. The number 52 comes from the total number of cards in the deck. So I have 52 cards in this deck here. And for spade, that represents all of these cards at the bottom. So there's 13 of these cards at the bottom, so that's how I get this 13. The probability of getting a royal card, all right, so where are my royal cards? So I have 3 royal cards here at the top, Jack, Queen, King. But I also have 3 over here, I have 3 over there, and 3 at the bottom. So 3 plus 3 plus 3 plus 3 will give me a total of 12 royal cards. And finally, I need to minus the situation where they're common, which is spade and royal, and that's going to be 3. So if I look at my bottom row right here, these are my spades, and 3 of them, 1, 2, and 3, those are considered spade and face cards. So there's 3 of them out of a total of 52 cards. So that's how I get the 3 there. All right, and then you can go to your calculator here and you get 22 divided by 52. And if you simplify that, well, fine, 22 divided by 52. All right, next question. What is the probability that the card is less than 8 or a heart? All right, so if you're less than 8, those are numbers like 7, 6, 5, 4, 3, 2, and ace is also included. So what's the probability that the card is less than 8 or a heart? Okay, so can a heart be less than 8? Let's take a look. Let's move this up here. Okay, so before we break this problem down, is this a mutually exclusive or a non-mutually exclusive problem? Well, if you look at your hearts right here, which is your 3rd row, can you have a heart that's less than 8? And the answer is yes. I mean, this is less than 8, that's less than 8. These cards right here to the left of 8, these are all less than 8, and they're all hearts. So what that means is this is a non-mutually exclusive problem. And if you have a non-mutually exclusive problem, then you can use the formula from above here. You want to have the probability of a heart plus the probability of being less than 8 minus the common area, which is probability of heart and less than 8. All right, so the probability of being a heart is 13 out of 52. The probability of being less than 8 is 28 out of 52. And the probability of being a heart and less than 8, that's going to be 7 out of 52. So once again, let's talk about how we got these numbers here. Let's bring out the deck. The probability of being a heart, well, the hearts are right here in my 3rd row. and I have 13 of these hearts, so that's where I get the 13. And once again, the 52 is the standard 52 cards in a deck. The probability of being less than 8. Now this one might be a little tricky, but if you look at your deck right here, let's focus on the bottom row, the spades. Basically, the cards that are less than 8 are cards such as 7, 6, 5, 4, 3, 2, and the ace. So if you count all these cards from ace to the 7, those are actually 7 cards. And then if you look at your next category, the hearts, you also have 7 cards that are less than 8. And then if you look at the clubs, for example, you also have 7 cards that are less than 8. And then for the diamonds, you also have 7 cards that are less than 8. So 7 plus 7 plus 7 plus 7 will give you 28. So 28 out of the 52 cards in the deck are less than 8. And then finally, the probability of being a heart and less than 8. Well, here are your hearts, the third row right here. And there are exactly 7 cards that are less than 8. So the ace, the 2, the 3, the 4, the 5, the 6, and the 7. Those 7 cards are less than 8. All right, and then you can go to your calculator here, and your final answer would be 34 divided by 52. All right, let's move on. All right, let's take a look at another Venn diagram problem. Assume that all students must take math and science, which is good. The probability of passing a math test is 70%, and the probability of passing a science test is 80%. Find the probability of passing both tests is 65%, and I want to find the probability of each event. So I have 3 situations. Student passes math but not science. Student does not pass both tests. And finally, the student passes math or science. All right, so for this question, we need to draw a Venn diagram. So here's my Venn diagram right here. The red circle will represent math, and the blue circle will represent science. Now, when we solve this kind of a problem, we need to take the information from the problem and put that information into our diagram right here. And this second to last line here, the probability of passing both exams is 65%. So the probability of passing both tests is 65%. So this 65% will represent this region right here. All right, this is the region where you can pass both math and science. So this region right here is 65%. Now, once you know that this is 65%, you need to calculate the probability of passing math only and the probability of passing science only. Now, if we know 70% of the students pass math, the math test is 70%. Okay, so we know that the probability of passing math is 70%. And so given the 70% and the 65%, how can we find the probability of passing math only? Well, that's going to be the 70% minus the 65, and that's going to give you a total of 5%. And you'll notice that if I have 5% plus 65%, that represents 70%, which matches the question. The probability of passing math is 70%. All right, now we need to find out the probability of passing science only. So the probability of passing science is 80%. From that 80%, 65% have also passed math. So in order to get this region here, I need to take my 80 minus my 65, and that will give me a total of 15%. So 15% people pass science only. That's what this 15% means. And 65 plus 15%, that represents 80%, which tells you the number of students who did pass science. Okay, so let's get on with the questions now. What's the probability of a student passing math but not science? Okay, so that's the same thing as saying the probability of math and not science. So you pass math, but you fail science. Well, basically the 65%, this represents passing math and science, but this 5% means passing math and not passing science. So this will be 5%. All right, so that 5% means you pass math, but you did not pass science. You pass math only. All right, the next question. Student does not pass both exams. Okay. So what's the probability of not passing math and science? Now for this problem, we can use the complementary or the complement theory, or sorry, the complement principle, and that's the same thing as 1 minus the probability of math and science. And using this situation, it'll be a lot easier to solve that. So the probability of math and science, that's going to be 65%. So I can do 1 minus 0.65, and that'll give me a total of 35%. So there's a 35% chance that the student will not pass both exams. And finally, question number C, what's the probability that the student will pass math or science? All right, so since they do have a common area here, this is a non-mutually exclusive problem. So I can use the formula that was taught in the lesson, the probability of math plus the probability of science minus the probability of both. Well, the probability of passing math is going to be 70%. The probability of passing science is 80%, and then I want to minus the common area, which is 65%, and that will give me a total of 95%. So there's a 95% chance that the student will pass math or science. All right, let's move on. Final problem of the lesson. The results from a marathon is recorded. 35% of the runners took more than 3 hours, 40% less than 2 hours, and 10% finished within 1 hour. Find the probability of the following. Okay, so I guess we have a running problem. I want to know the probability for a runner that takes between 1 and 2 hours, and I also want to know the probability for a runner that takes between 2 and 3 hours. Okay, so let's draw a little diagram again. So in my diagram, I have a situation where I'm more than 3 hours. I have a situation where I'm less than 3 hours. And pretty much if I've taken more than 3 hours, so that's going to represent 35%, because it states 35% of the runners took more than 3 hours. So this outside region right here in white, this represents more than 3 hours, so that will be 35%. All right, then I have 40% less than 2 hours and 10% finished within 1 hour. Okay, so let's take a look here. Now, if I have a situation here, you're less than 1 hour. Less than 1 hour is also included as less than 3 hours. These things can happen at the same time, so they're non-mutually exclusive. Because if you finish less than 3 hours, then you've also finished less than 1 hour. Okay, so let's take a look here. This will be 10% because 10% finished within 1 hour, so that represents 10%. So then how many people would finish less than 3 hours only? So if 40% finished less than 2 hours, then that would mean less than 2 hours, this would be 30%. 10% plus 30%, that would give you the 40% less than 2 hours. And 10% finished within 1 hour. Okay, so now that I've got a basic little diagram right here, let's try to break down the problem. The runner takes between 1 and 2 hours. Okay, so if you're between 1 and 2 hours, that means what's the probability that you're greater than 1 but less than 2? And that's simply going to be 30%. This 30% means that you're less than 2, but you're not in the 1% region, so that would be 30%. All right, finally, the runner takes between 2 and 3 hours. Okay, so what's the situation that you're in this region right here, this yellow region, between 2 and 3 hours? So this is a good question to kind of think about, but the answer is going to be about 25%. So the answer is 20%, and how do we get 25%? Well, I know that 35% of the runners took more than 3 hours, but 40% of the runners finished in under 2 hours. So that means if you're between 2 and 3 hours, what's the missing region here? Well, if you have 100% minus 35% minus 40%, that will give you the 25% there. All right, so that concludes this lesson, and we'll see you again for the next lesson.